After studying the infinite potential well, you might want to study a more realistic one, the finite potential well. This is a potential that is zero everywhere except from x equals to negative a to x equals to positive a, where it takes the value of minus v naught. These conventional values will make it easier to split the problem into bound solutions, those for which the energy of the particle is negative, and the scattering solutions, those for which the energy of the particle is positive. Let's first find the solutions for the bound states, those for which the energy of the particle is negative. So the particle has an energy between that of the potential and zero. As in previous solved problems such as the infinite square well of the harmonic oscillator, we want to find the allowed energy states. We are looking for those eigenstates of the Hamiltonian. In the present problem, we can differentiate three regions: x smaller than negative a, x between negative a and positive a, and x greater than positive a. For the first region, Schrödinger equation can be written as minus h bar over 2m times the second derivative of the wave function with respect to x twice equals the energy times the wave function. We can make some definitions here to simplify this. We call the Greek letter kappa to the square root of negative 2 times m times the energy E over h bar. Be careful and don't get confused with the negative sign, as the energy in the bound state is negative, so kappa is real. This Schrödinger equation then reads as the second derivative of psi with respect to x equals kappa squared times psi. This is a simple differential equation whose solution is an exponential. The exponent of the exponential could be positive or negative, but the negative exponent in this region does not converge to zero due to the fact that x in this region is also negative. So this is not a physical solution, as it's not normalizable. The other solution, on the other hand, behaves well, so we can write that the solution to the bound state in the negative region is psi equals to b times e to the power of kappa x for x smaller than negative a. Before I find e, I will find the solutions for the other regions, and then imposing continuity of the wave function and its derivative, I will find the normalization constants. Let's go to the region of the potential well, x between negative a and positive a. Here, Schrödinger's equation reads negative h bar over 2m times the second derivative of psi plus the potential times psi is equals to e times psi. But because the potential is negative, we write v as negative v naught. I can move the potential term to the right hand side, and now I will do another definition of variables. I will call L equals to the square root of 2m times e plus v naught over h bar. Let's pay attention to the signs here. The energy is negative. Remember that we are solving for the bound states. V naught is a positive number, which is also in absolute value greater than e. Therefore, e plus v naught is a positive number. We see then that L is also a real number. Here then, the Schrödinger equation is an old friend for which we know the solution, which are trigonometric functions. The general mathematical solution is z times the sine of Lx plus d times the cosine of Lx. Look, here that the potential is symmetric. That means that the probability density function is also going to be symmetric, which lets us with the wave function either even or odd. With this, we can split these solutions into even solutions or odd solutions. But looking at what we just found, the cosine is even and the sine is odd. So we can say that either z or d will be zero, depending on which solutions we are considering. Most textbooks, such as Griffith's, solve the even solution and let the odd solution to the reader. I'm going to solve the odd solution here. The odd solution in the range from negative a to positive a is d times the sine of Lx. Now we go to the third region, that for which x is greater than positive a. But we need not solve this as we already did. Remember that symmetry of this problem. Whatever solution we found for x smaller than negative a has to be the symmetric to what happens for x greater than positive a. The physical solution in this case is psi equals to f times e to the power of negative kappa x. Remember that kappa is positive and x is positive in this case, so now we can write the whole solution. Psi of x is equals to f times e to the power of negative kappa x for x greater than a d sine of Lx for x between minus a and plus a and minus c sinus of x due to the symmetry for x smaller than minus a. I have to apply continuity to two places, x equals to a and x equals to negative a. Looking at the solution, this gives me f times e to the power of negative kappa a equals to d sine of La. Also, the continuity of the first derivative imposes that minus f times e to the power of minus kappa a is equals to d times L times the cosine of L times a. We can divide one by the other and find that minus kappa is equals to L times the cotangent of L times a. Now, I am going to introduce another definition to simplify this a bit. I will call z to L times a, which is equal to a times the square root of 2m times e plus v naught over h bar. Remember that e is negative. And I will call z naught to z when e is equal to 0. So z naught is a over h bar times the square root of 2m v naught. If we square z naught and z and subtract one from the other, we have that a square over h bar times 2m v naught minus a la square, which is a square over h bar squared times 2m times e plus v naught, which is then a square over h bar squared times negative 2m times v naught, which is just kappa square a square. With these new relationships, let's go back to the equation we derived imposing the continuity equation conditions. I'm going to multiply it by a. Look at the left-hand side of the equation. This, in fact, is kappa a, which is the square root of z naught square minus z square. And the right-hand side is minus z times the cotangent of z. Or divided by z, we get the square root of z naught over z squared minus 1 is equals to the minus cotangent of z. Well, after these wobbly, timey, mathy manipulations, we have found one equation of one variable that contains the continuity constraints that the wave function needs to satisfy. We now only need to solve this equation to find the allowed z values. But before we get there, let's try to understand what is this z value. Z is the parameter that contains the information of the size of the potential well. It's linearly proportional to the width of the well and proportional to the square root of the energy gap between the particle and the depth of the well. Remember that E is negative, so E plus V naught is the distance from the energy of the particle to the bottom of the potential well. So Z squared would be proportional to the area of the square well and the energy gap. The bigger the Z, the bigger the well, and the smaller the Z, the shallower the well. This Z is unit-free, and I let you check it out. Solving the last equation for Z means finding the energy values allowed in this system. We will solve this equation graphically. We can plot the left-hand side of the equation versus the right-hand side of the equation and find the crossing points. Here is the graph of the cotangent of Z in red and the graph of the square root of Z naught over Z squared minus 1 in blue. In this plot, they cross at several points marked with the circles. These are the allowed solutions of the energy of the system. These are specific Z values. But remember that Z depends on the mass of the particle, the potential depth, the width of the well, and the energy. Solving for the energy, we find the allowed values of the energy. We have found the quantized allowed states for the odd solutions to the finite well potential. Now, for the plot, I gave a value of 5 pi over 2 to Z naught, but if I decrease and make it 2, we are making the well more shallow. Then the whole plot goes down and there is only one solution, one crossing point. If I make Z naught greater, then the well is deeper, then the plot goes up and there are more solutions to the potential. In the case of the even solution, there will always be at least one crossing point, one solution. In the case of the odd solutions, we might see that if we make the well shallow enough, there will be no crossing, so no odd solutions to this problem. Well, now we should go and solve the scattering states. But before that, let's have a look again at the wave function for the bound states. We have a wave behavior inside the well and an exponential decay behavior out of it. As the energy is negative, classically the particle would not be allowed to be out of the well. But here we see that the probability of finding the particle outside of the well is non-zero. That probability decreases exponentially with the distance from the well. We could calculate what is the probability of finding the particle outside by integrating c star c from negative infinite to negative a and from a to positive infinite as usual. If there was a second nearby potential well, the particle could tunnel to it. It could be in one of the wells and then by tunnel effect be in the other one. This without enough energy to jump, escape and get into the second well. This is classically prohibited, but quantum mechanically this is possible. The waviness behavior inside the well is similar to that in the infinite square well, and this waviness is lost out of the well. Now, if we calculate the scattering states, we consider the energy E to be positive. The solutions to Schrödinger equations are similar to the bound state. Again, we should apply the boundary continuity conditions at A and minus A. This gives us 4 equations to determine the parameters A, B, C, D, and F. The reason why I only consider the F term and not G term is that I am considering the particle flying from the left towards the well. Once it reaches the well, it can be scattered backwards or forward. I assume there is no particle coming from the right of the well. It is practical in this type of situations to define the transmission coefficient and the reflectivity coefficient. Transmission coefficient is defined as F squared over A squared absolute value. This is the ratio of the coefficient associated to the outgoing wave, leaving the well to the right and the coefficient of the incoming wave. With all these we have seen so far, we can attempt to solve the step potential, a potential that is 0 for negative x and V0 for positive x. Let's consider a particle with lower energy than the step in the region that the potential is 0. We expect the wave function to be waviness. For the region where the potential is V0, we expect the behavior to be a decaying exponential. Continuity of the wave function at the boundary implies that a plus b is equal to f. Continuity of the derivative of the wave function, the boundary implies that ik times a minus b is equal to minus kappa f. Solving the system of equations, we can find that the reflectivity coefficient is equal to 1. This means that even though the particle can penetrate the barrier by tunnel effect, at some point all the wave function is going to be reflected back. You can solve the case where the energy of the particle is higher than the barrier.